Welcome back. It is day 5, I believe, and we're doing ordinary differential equations. So yesterday we did more on the Wronskian, which is just this determinant that we can use to find if a solution is a general solution. That's yesterday. We don't need to worry about that. If you care, go watch it or learn it, better yet. But today we are going to be learning non-homogeneous differential equations, or I will be learning. I guess we're just gonna go right into it, which has the general formula y prime prime plus p of t y prime plus q of t y equals g of t. My pen is still broken. I can't use my drawing tablet, so I'm using my mouse still. I really want to get this thing fixed because I don't enjoy using this mouse. What we can see here, though, obviously, is that we're not dealing with constant coefficients again. Oh, and it looks like they're defining a homogeneous differential equation. Oh, okay. So this is our non-homogeneous differential equation. This right here. But they call this the associated homogeneous differential equation to 1, which they define as y prime prime plus pt of y prime plus qt y equals 0. It looks like they're doing just the same thing, except removing that g of t, which makes it non-homogeneous. They're going straight into a theorem now. Alright, we have to label these, I guess. So that's 1, that's 2. So we have two solutions, y1 and y2 for not 2 but for 1, our non-homogeneous differential equation. So they're both those are two solutions for our non-homogeneous differential equation, and we have two solutions, y1 and y2, which are fundamental set of solutions for 2. And apparently what they're trying to say is that y1 minus y2 are solutions for the non-homogeneous differential equations. Our non-homogeneous differential equation can be written as c1 y1 plus c2 y2, which is just our general solution for homogeneous differential equation. Because it's our general solution because y1 and y2 are fundamental sets of solutions, which is given to us. Oh, and they finally and they decide to prove it too, which is really nice. So what we're proving is that y1 minus y2 is a solution. So it looks like so we're going to plug it into our associated our associated homogeneous differential equation, and then all we do, we've done stuff like this before, or I have. If you've done differential equations, then you have too. We just plug this into, or we just combine like terms, so we would then get y1 prime prime. Okay, they're expanding this out weird, but I'm gonna take their word for it because it's not very enjoyable to write very much. I'm gonna write as little as possible with this mouse. So plus p of t y1 prime plus q of t y1 minus. Expand that out weird, but then what they're trying to say is that this becomes, I'm not sure where the gt is coming. I might have to actually check this now because this doesn't seem very intuitive. But what they're saying is that now we're getting gt minus gt, which is equal to 0. Or those cancel out, so 0 equals 0. Okay, so I'm not entirely clear on the reasoning. So basically what they're doing, plug it into our associated homogeneous differential equation. We plug in y1 minus y2, and what they're trying to do is they're trying to turn this into two second-order differential equations. And what it looks like is that you can turn both of these into g of t, because of our original equation y prime prime. This right here can pretty much become, or g of t can substitute. This is what I think they're trying to get at. What I am unclear about is how y1 and y2 can both equal gt. I get they're both solutions. Never mind, they're both solutions, so of course they would both work to get our g of t. So because they're both solutions, if you these should both equal g of t, given that we're dealing with the same constants and everything's the same pretty much. So of course, and immediately below the proof was the reasoning. which I had to just figure out on my own just now. I should have just kept reading. So what we just proved then was that the two solutions for the non-homogeneous differential equation, that those are a solution to the homogeneous differential equation, which is written in the form c1y1 plus c2y2, or in other words, this equals this. That's what we pretty much just proved. Okay, so what they're trying to say now, we're using this identity, or not identity, I guess it's kind of an identity, but we're using this formula right here now. And what we're going to say is that y of t, this is going to be our general solution to 1, and we're going to say that y sub p of t, this is going to be any solution to 1. Okay, and so using our original theorem, we can then say that y of t minus y sub p of t, this is going to equal c1 y1 plus c2 y2, or in other words, our general solution is going to be equal to our solution to the our associated homogeneous differential equation plus any solution to the non-homogeneous differential equation. And we're defining, okay, and they try to make this an even shorter formula. So they call this the, what do they call it? They call it the complementary solution, and y sub p is the particular solution. So they're just trying to be able to write it shorter. So now it's y sub c of t plus y sub p of t. And wait, that's it. That took no time at all. There's no examples. It seems like this is just part 1 of a much longer. Can I do another section? The next section is so long. Oh my gosh. I'm gonna leave that for today. So that was super short, but this gives me time for group theory. So if you're interested in that, I will be uploading another video soon on group theory. Or not soon, today. If you're watching this the day this video has come out, I will be doing another video on group theory, hopefully. Here's the final result. Goodbye.